In this demonstration, we present dHive, a visual analytics system for query execution performance analysis via Dataflow in Apache Hive. Apache Hive has been widely used for big data analysis. In Apache Hive, the SQL-like statement named HiveQL is first translated into a logical execution plan, which consists of map or reduce jobs. Massive tasks are spawned from each job as the basic execution units. These tasks are then scheduled to run on different machines. For engineers and developers with Apache Hive, answering the question of, where does time go in Hive query execution, is important to analyze and identify the performance bottlenecks of query execution. However, answering this question is difficult because various factors could affect system performance, such as the resource competition, unbalanced data layout, and data skew. The complex execution process brings a significant challenge for analyzing time consumption. To facilitate query execution analysis, we have designed dHive, a visual analytics system that traces the details of query execution process. In dHive, the task execution process is presented as a data flow, which is a transition of data status from prepared to output. The data size is encoded using the height of the data flow. Each job execution process consists of several task data flows. By stacking the task data flows along the time axis, we can obtain the job data flows as well as the overall query data flow. dHive enables users to explore the execution process via data flow at multiple levels. We will demonstrate how dHive can be used to diagnose performance problems. First, Query Selection View allows users to choose a query for further analysis. Here we select Query 29 as an example. After selection, basic execution information will be presented, including execution time, data size, and the number of containers. In addition to Query Selection View, dHive offers three other coordinated views: Query Logic View, Dataflow View, and Processing Details View. In Query Logic View, a Gantt chart-based visualization is used to display the query logic. Each node represents a map or reduce job, with left and right positions aligned with the job's start and end time. Nested rectangles in each node are colored red, green, and pink to represent the input, computation, and output time usage for each job. Job dependencies are shown as links. In Dataflow View, dHive illustrates the query data flow in the top half, displaying the total, prepared, unprocessed, and output data during execution. It also highlights the crucial operators, such as the filter and join operators. The Job Dataflows view at the bottom presents the job dataflows and their dependencies. Processing Details view reveals overall parallelism and processing details of each task. In this view, each row represents a container from Yarn, and rectangles represent tasks executed by the container. Red and blue colors encode normalized input and processing speed of each task, with darker colors indicating the faster speeds. In this example, we find that jobs M1 and M8 have longer execution time in Query Logic View. In Dataflow View, they both have long tails, which indicates slower data processing speed at the job level. We select M1 for further analysis by clicking on it in Query Logic View. Upon clicking, we can see M1's execution operator tree appended in Query Logic View, and the data transformation matrix between different machines is appended in Job Dataflow View. Moreover, in Processing Details View, the parallelism of selected tasks is shown at the top, encoded with yellow color, and all the tasks from M1 are also highlighted. Counter information of M1, ordered by the degree of values dispersion, is presented at the bottom. Upon reviewing M1's tasks, we notice that several tasks from different containers have longer execution time, such as the last task from container 0851. We also found the red color of this last task is lighter than the other tasks on the same line. After clicking the last and the first task from container 0851 for comparison, we observe that the first task runs for 2.3 seconds with a much higher input speed throughout execution, while the last task takes 17.2 seconds with significantly slower input speed. However, the data processing speed of these two tasks is quite similar. Another distinction is the data source. the slower task needs to fetch data from DBG03, whereas the faster task fetches data locally from DBG08. Hence, we can speculate that the longer execution time for the last task is caused by the slower input speed, and the transformation overhead from the network may be the root cause of this issue.